sun is driving me nuts. Okay, better. I need what? I need that one I want in my pictures. Yeah, I do. I thought I did.
I'll explain in a moment, but I'm passing this out. Okay, so next week, I will not be here on Tuesday. I will be back on Thursday. So you have a choice. Originally, we were scheduled to have a lecture on Tuesday and a test on Thursday. I'm giving you the choice. Dr. DeRocher, who was the one that took the lecture when I was gone previously, would be taking this lecture as well. We can either continue with the same schedule but Dr. DeRocher would give the lecture, and then I would give the test on Thursday. Or if you want to flip so that I'm giving you the lecture, then you can have your test on Tuesday and I can lecture on Thursday. I don't want to put any pressure on anybody, so that's why the card. You got choice A or choice B for next week. You will have a test on one of the days, you will have a lecture on the other day. Just depends on who you want to give the test, who you want to give the lecture. That's it. The test will be written by me, one way or another. The material will end today, one way or another, because I'm going to finish up a overall concept today. So it does not matter from that perspective. You will still have at least a week to study for your test. But the question is, who do you want to give the test and who do you want to give the lecture next week? Any questions before you decide?
The test on stuff that we're doing in August this week.
The test, that will be part of it, yes, because we've already covered that. So the test will include all naming. Now, I won't have naming ions by themselves, but I will have naming ionic compounds on this test as well. So it'll include all the naming. It will include calculation of molar mass and formula mass. It would include those conversions, dealing with Avogadro's number, molar mass, and formula mass. Well, molar mass and Avogadro's number. And it will include Lewis structures, VSEPR, valence bond theory, molecule polarity, and then the stuff we're going to go over today, which includes bond length, strength, and polarity, and then lattice energy trends. So it's a heavy duty exam one way or another. ed puzzles. It will not be over the ed puzzles that will be at the end of the week, just the ones that were due yesterday. Other questions? So that you don't have to worry about which way, like I said, these are your two options. It basically is determining who gives the lecture. The material will stop today one way or another. I will say I will not be able to go back over whatever Dr. DeRocha lectures on. So it'll be, if you choose A, it will be final. I'll have to continue from there. Okay, so I want you to fold your little card in half, because I don't want to know, that's the reason for this. I don't want to know anything. And I'll come around and grab them, and then I will let you know. I always have to say when I try to change anything up, so that's why I'm making sure you get your say. Did I get all the cards? I'll tell you real quick what it's going to be, because it won't take me long. Okay, overwhelmingly, A. So Dr. DeRocha will be lecturing. He will be going over he should be going over stoichiometry and limiting reactants, if I recall correctly. And then I will give you your test on Thursday, according to how it was voted. Okay. So now we will get into today's material. Before I really get into today's material, I just want to quickly recap some of the things that we did over the past week and a half. We started with, well, I guess it may have been a little longer. I don't know, because of fall break. But let's just go over some of what we've done since last test. Really starting with the last test, that's when we really got into the formation of compounds. We were talking about how to name ionic compounds. We were talking about how to name covalent molecules. And we talked about how to name acids. Once we finished with that naming, we did talk about calculations of formula mass, where you were dealing with a single molecule, and molar mass, where you were dealing with 6.022 times 10 to the 23rd of them.
And we did some conversions dealing with molar mass and Avogadro's number. But those conversions were still about the compound and the elements within that compound. After that, we started looking at what those compounds actually look like. We started with the Lewis dot structure of an atom of an element, and we allowed those atoms of the elements to combine to form the compounds. In the case of ionic compounds that had ionic bonds, those electrons on the metal were completely removed and donated to the non-metal or metalloid to make ions. But we did not show a bond because in an ionic compound, it is just an electrostatic attraction between the cation and the anion. After we did ionic compounds, we then moved on to start talking about covalent molecules. And in covalent molecules, as well as polyatomic ions, we did show the bonds. Because in those particular cases, within the covalent molecule, within the polyatomic ion, the bonds arise through the sharing of electrons between two atomic nuclei. And we really started talking about the making of those bonds. Once we developed Lewis structures, we then moved on to talk about the shape of the molecule, which is how we use VSEPR theory. VSEPR theory describes the shape of the molecule. And we talked about its electron geometry, we talked about its molecular geometry, and we talked about the ideal bond angle. From there, we use valence bond theory because if you simply look at atomic orbitals are incapable of explaining the molecular shapes. In the case of atomic orbitals, if you have p orbitals, they're at 90 degrees from one another. If you just looked at atomic orbitals, there would be no way for a carbon to make a tetrahedral compound. If you just looked at atomic orbitals. So we talked about hybridization using valence bond theory. And specifically, we figured out the hybridization that occurred on the central atom in order to get those molecular shapes. After we talked about valence bond theory, another piece that came out of that is sigma and pi bonds. The first bond between any two atoms is a sigma. If there are additional bonds between the same two atoms, those are pi. And that basically describes whether there is direct overlap or side-to-side overlap. And then finally, we talked about the molecule's polarity. Basically, if we see a trend in the electronegativity where it's increasing in one direction, that means that the molecule is polar. But if we look at the electronegativities and we do not see a trend in one direction, that means that the molecule is nonpolar. So we really got into the molecules, basically. We took those names and formulas and we really got into the molecules to see what they looked like, is what it boils down to. Now, there is one more thing we need to talk about with respect to these covalent bonds that were formed and the ionic compounds that were formed. So today, the first thing we're going to talk about is going to be bond length, bond strength, bond polarity, which the videos on Thursday alluded to. And then finally, we're going to talk about lattice energy. The first three of these will be directly related to our covalent bonds, whereas this last one is related to the ionic compound. Now, before we get into that, I also want to talk about a couple of other things that we've talked about. So folks, whether a molecule will form or not is all based on energy. We can predict the shape of a molecule. We can predict the bonding. But if the energy does not say it will occur, then it will not occur. Everything comes back down to energy. And so I just wanted to bring up a couple of things because this is going to come into play. First of all, when we start talking about bond strength, we're going to be talking about energy. And then when we get into lattice energy, we're going to have to come back to ionization energies to form the cations and electron affinities to form the anions. So when we get there, we're going to get back into those energies as well. So basically, again, if the energy doesn't, if you have a molecule and the energy does not say it will occur, then it's not going to occur because the energy is the driving force. So what we're going to do is we're going to take and we're going to look at some of these molecules or some of these bonds. Okay, so let's just talk about a hydrogen-hydrogen bond. A hydrogen-hydrogen bond has a bond strength in kilojoules per mole of 432 kilojoules. Literally what that is telling you is to break that single bond, you have to put in 432 kilojoules of energy. So kind of think about breaking a stick over your knee. You got to put energy in to break that stick. The same thing occurs with our bond. You got to put energy in to break the bond. And for hydrogen-hydrogen, that's 432. Now, as far as the bond length, let me do it this way so that I can take and write on this. So as far as the bond length, what does this 774 picometers mean? What it means is if you have a two hydrogen atoms, that 74 picometers is describing the distance between the two nuclei. So for a hydrogen atom and a hydrogen atom, the distance between those two atomic nuclei is going to be 74 picometers. Now, what I want to look at now is I want to look at the HF bond, the HCl bond, the HBr bond, and the HI bond. And I want us to look at bond length first. So we're going to be looking at this far right-hand column first. What do you notice about the bond length between hydrogen and fluorine, hydrogen and chlorine, hydrogen and bromine, and so on? They get further and further apart. Now, why would they get further and further apart? Shielding, which causes what? Bigger atoms. So in other words, we can say the larger the atom, the longer the bond. The larger the atoms in the bond, the longer the bond. Now, go back and look at our bond strength. And what do you notice? The strength decreases down a group. So what you can say is that the longer the bond, the weaker it is. So these two things are inversely related. Shorter bond, stronger bond. And again, this bond length is all due to atomic size. Questions about that? Okay. So now what I want to do is I want you to first look at this one, which is our carbon-carbon. So carbon-carbon is 347 and 154. Carbon, single bond carbon is, let me see if I can actually make this work right. I can almost. Oops. This way I can write on it better. What I want you to look at now is I want you to look at the carbon, single bond carbon. I don't want that. Let's just underline it. I want you to look at the carbon double bond carbon. And I want you to look at the carbon triple bond carbon. We already know the longer the bond, the weaker it is. So let's stay to that concept. The longer the bond, the weaker it is. So let's focus on bond length, which is the far right column. What do you notice about bond length with respect to single, double, and triple bonds? It's decreasing. A triple bond is shorter than a double bond, and a double bond is shorter than a single bond. If a triple bond is shorter, and the shorter the bond, the stronger it is, that means that if a triple bond is shorter, it is also stronger. Okay, so let me summarize this over here. So when I look at the bonds, the first thing I do is I sort by type. Because the triple bond will always be shorter than a double bond, which will be shorter than a single bond. That is always going to be the case. I don't care whether it's carbon-carbon or carbon-nitrogen. If you got a triple bond, it's shorter than anybody else. And since it's shorter, it's always going to be stronger. So this is the first thing I sort by when I'm given a group of bonds. Once I've sorted them by that, the second thing I sort by is atomic size. Because the smaller the atom, or atoms, I should say, the shorter the bond. And all of this leads to the trend which is the shorter the bond, the stronger the bond is. So folks, if you haven't noticed, you got to remember your atomic size trend. From previous. And your atomic size trend is that if you look at a periodic table, as you go down a group, size increases. As you go left to right, across the period, size decreases. You got to remember those atomic size rules from previous. Yes.
So I think on the last test I got confused. So like say, we'll pick your one, and then it's cesium.
Okay. Cesium. Okay. So if you're looking at krypton and rubidium by themselves and they are neutral, then rubidium's larger. But what I think you're talking about is when rubidium made an ion compared to krypton. And once rubidium loses its electron to be isoelectronic with krypton, then it's actually smaller. Because cations are smaller than their neutral atoms as long as they're isoelectronic. So I think that's where you got it twisted. Because I think that's the problem I gave you, not rubidium by itself and krypton by itself. Because if those were just neutral, then yes, rubidium would be larger because it's further down. But one of them wasn't neutral. Okay, so how would you see this on an exam? You could see this in one of two ways. I could give you two at a time, or I could give you a series. So we're going to give you a series because that would be the hardest of the types. Okay. So place the following bonds in order of decreasing strength. So that means I want the strongest first and the weakest last. And from our trend, we know that the strongest means the shortest, whereas the weakest means the longest. The first thing I would do, I told you the order, is I'm going to separate it by type. So the longest is going to include the CC and CBR. The shortest is going to be the C triple bond N, and the C double bond O and the C double bond S are in the middle. So I sorted it by type. I haven't put it in order yet. All I did was sort by type. Yes. I meant BR. I sorted by type. Now, within each type, I will go further and sort by atomic size. So C triple bond N will be our first one. That's going to be the strongest and the shortest. Now, between C double bond O and C double bond S, O is smaller than S. Since O is smaller than S, it is going to be shorter than S. And so it will be stronger than S. And then I'm looking at CC and BRBR. Again, carbon is smaller, so it is stronger than the bromine. So this would be the order you would record your answer. Again, I sorted by type first, and then I sorted by size. Notice one thing, it didn't matter that sulfur was in period 3 and carbon was only in period 2. Carbon is smaller than sulfur, but because of that double bond, that C double bond S is stronger and shorter. It's the double bond that is pulling it closer together. So that's why you sort by type first, and then sort by atomic size second. Questions? And folks, this makes sense. Why? If you think about it, take one stick and break it over your knee. Okay, doable. Now take two sticks and break it over your knee. It doesn't matter what the length of those sticks are, it's going to be harder to break over your knee. Because you got two of them, and now take three, and it's, depending upon the diameter, can be quite difficult to break over your knee. So a triple bond is going to be a stronger bond no matter what. Questions? Because this is bond length, bond strength in a nutshell. That's all there is to bond length, bond strength. Are there going to be exceptions to the trend? Yes. This is a trend, not a rule. Not a, you know, it's not finalized for everybody, but it is a common trend. There's always exceptions to everything. I hate to say it. This is a trend. And I will be looking for the trend on the test because you're not going to have the bond table on the test. Now, let's get into bond polarity, which was alluded to in the movies on Thursday. When we talked about molecule polarity. First of all, let's talk about what bond polarity means. So let's say I do have a hydrogen-hydrogen bond. Now, what you have to remember with hydrogen, with any bond, yes, we draw those electrons in a line and we draw them between two atoms. And it is very easy to think that those electrons are stuck between those two atoms. But the fact is, folks, electrons are not stationary. Electrons are constantly in motion. And because they are in constant motion, we can draw a density map. And if we drew a density map around our hydrogens, meaning the electrons are anywhere within the bubble, the electrons spend time anywhere within the bubble. If you draw a density map around your hydrogens, you would see that the electrons spend time evenly between the two atoms. They spend their time evenly. So yes, they're in constant motion, but it means that one's going to be over here, and one's going to be over here. They're just constantly moving around, but it's always going to have this an even distribution. Now, if we were to look at hydrogen and fluorine, we would not see an even distribution. If I drew a density map, what we would see is that the electrons spend a lot more time around the fluorine atom than they do around the hydrogen. They spend a lot more time because fluorine is a lot more electronegative than is our hydrogen. And electronegativity describes how much time or yeah, let's call it how much time an electron spins with a particular atom. In a bond. The larger the electronegativity, the more time the electrons spend with that atom. The larger the electronegativity, the more time the electrons spend with that atom. So fluorine being a 4, the electrons love fluorine and they're going to spend a lot of time around the fluorine. Now, what that results in is a high electron density on one side of the bond and a low electron density on the other side of the bond. Now, electrons are negatively charged. And if the electrons are spending more time around the fluorine, that means that the fluorine winds up with a partial negative charge, which will be represented with the Greek letter delta, which I cannot draw exactly the way, I think most of the time you'll see it written this way, almost like an S. Now, if they don't spend much time around the hydrogen, that means there's not much electron around the hydrogen. So the hydrogen end winds up with a partial positive charge, which again is going to be represented by the delta positive. Now this creates a dipole moment. And dipole moments, as we mentioned on Thursday, are represented with the arrow notation, where the arrow points towards the negative end and there's a cross on the positive end. I actually love to think about it this way because if I think about it as a cross, whoops, didn't mean to do that. If I think about it as a cross and this is also a cross, it makes sense that they go on the same side. That's how I keep it straight. So basically bonds have this opportunity. They can be non-polar, they can be polar, and they can be ionic. So how can we sort this? And the reason I'm giving you two different versions is it is directly dependent upon what textbook you use, which version you get. So I'm going to give you both. Because I have one that I say is a pure non-polar bond. And if it's purely nonpolar, that means that the difference in the electronegativities between the two atoms is equal to 0. Now you can also have just a non-polar. And in this case, the difference in electronegativities is going to be anything from 0.1 to 0.4. And yes, you are given your electronegativity table on the test. You don't have to memorize the numbers, those numbers. You got to memorize this design. Now, the difference between mine and active is that active just has one category for nonpolar. And it's anything from, the difference in electronegativity would be anything from 0 to 0.4. So it just combines my first two. Otherwise, once you get through the polar, non-polar, you now have polar bonds. The polar bond is a difference in electronegativity of 0.5 to 1.9, and that does not matter whether it's mine or active. And then finally, you have ionic, and that will occur if the difference in electronegativity is anything greater than, I should say anything greater than or equal to 2. And that is again true for either. So really, I only have one small difference. And that is, I like to call things purely nonpolar if they equal 0. Otherwise, they're identical. Now, folks, this actually can be confusing because some of the bonds that we once classified as ionic compounds, they can have polar bonds if we're strictly looking at the electronegativity. In fact, a lot of your transition metal compounds, the bond is closer to a polar bond rather than an ionic bond. A true ionic bond. But even the polar bonds, again, those atoms spend more time with one element than the other.
So if you're looking at these, yeah, polar, non-polar, non-polar, polar, and then, so those would be covalent bonds. Last one, you strictly have like an ionic.
Correct. There again, this is where it gets a little tricky because what you have to really understand is whether or not in making the difference comes down to a bond compared to a compound. And when you have like a sodium chloride compound, you have more than one sodium in the compound because it actually forms these nice crystals. So there's a little, this is where it gets tricky because you've got to separate bonds from compounds. This is strictly talking bond. Then you move to compounds, which can be ionic, they can be, or they can be covalent compounds. And even in those compounds, you have the same type of separation because you're going to have nonpolar covalent molecules when there is no trend in the electronegativities, meaning that all of those vectors, all of the bond polarities cancel out. You'll have polar covalent molecules when all of the bond polarities are additive in one direction. And then you'll have ionic compounds where we have that complete, where the electron is transferred from the cation to the anion. So again, it's a difference in bond compared to molecule.
So, again, you're going to get your table of electronegativities, which you actually have in the packet I gave you, which I actually have to find. Where's my table of electronegativities? Do I have it in here? I just know most of them by heart. I don't think I have a table of electronegativities in here. Oh yeah, I do, right there. So for instance, if I were to give you a carbon nitrogen bond, you would go look up the electronegativities for carbon and nitrogen. Carbon is 2.5, nitrogen is 3.5. No, I'm sorry, it's 3.0. The difference in this electronegativity is equal to 3.0 minus 2.5, or in other words, it's 0.5. According to the table that I gave you, this bond would therefore be considered to be polar. So what that means is if you have your carbon and your nitrogen, because of this difference in electronegativities, the electrons spend a little more time around the nitrogen than they do the carbon, which creates a polarized bond towards the nitrogen away from the carbon. So there is a slight dipole moment. The only time you use dipole moments is if you're dealing with a polar thing. Polar bond, polar molecule, that's when you use the dipole moment arrow. If it's non-polar, you don't use it. If it's ionic, you don't use it. You only use the dipole moment arrow if it's polar. So let's look at another example. Let's say I have FeF. Fe has an electronegativity of 1.8. F has an electronegativity of 4.0. The difference in the electronegativity is equal to 4 minus 1.8, which is equal to 2.2. So this would be considered ionic. which means in reality, the way I've drawn this bond is incorrect. It means in reality that the electrons are entirely on that fluorine. There's none on the iron. Questions? Correct. Ionic does not share electrons. Other questions? Okay. So folks, that is bond polarity. That is bond length and bond strength. Any questions finishing up that piece?
I say that if you have like a central atom, and it's like smaller, like the difference in polarities.
So first of all, if all three outer atoms are different, or is it the three outer atoms are the same but different than the central? Okay, so if all outer atoms are different, it is going to wind up being polarized. It may not be strongly polarized, but it would be polarized towards the more electronegative of the atoms. Typically, you don't run into that case. You might have one that's different or two that's different, but there's not going to be a big difference. You'll have a lot of them that are the same, so it's going to be pretty obvious where the polarity is. But I mean, technically, I guess you could have that. It's just very unlikely. But anytime you've got a compound where all of the outer atoms are different, or any of the outer atoms are different, there is going to be a polarity for a molecule. Okay, let me erase all my drawings on this so I don't have to go find this again. And let's move on to lattice energies. Now, I am not going to expect you to calculate lattice energy, but I am going to look at lattice energy. And what I want to do, okay, so that should be okay. I'm going to do what I've been doing so I can scribble on it. Okay, so this is illustrating the formation of sodium chloride. Now, sodium is a solid. And we talked about the fact that chlorine is one of our diatomic molecules. Now, in order for sodium chloride to form, you have to take the sodium and we have to get it from solid form into a gas, and then we can ionize it. To get our chlorine, we've got to split the chlorine, and then we can ionize it. Now, to take a solid, let's just talk ice. If I want to take ice and get it from ice into steam, what do I have to do? Heat it up. I got to add energy to it. To take sodium solid and get it into sodium gas, you've got to add 107.3 kilojoules of energy. This would be the energy associated with sublimation, a solid going into a gas. Now,
To take that chlorine molecule and get it into a chlorine atom, I've got to break the chlorine-chlorine bond. And we just talked about the fact that to break bonds, it requires energy. This is going to be bond association energy. And it's 122 kilojoules. Then my sodium solid is now in sodium gas. I can take that sodium gas and I can use the ionization energy to convert that sodium gas into sodium ion. But I'm going to add 495.8 kilojoules of energy. My chlorine, we got it into chlorine gas in atomic form, but we got to take that chlorine gas in atomic form and we got to give it to chloride. That is the the electron affinity. And the electron affinity for taking a chlorine atom and converting it to chlorine ion is a negative 348.6 kilojoules of energy. Now, if you look at, ignore this arrow for now, if you look at steps 1, 2, 3, and 4, and you were to add up steps 1, 2, 3, and 4, the overall energy associated with steps 1, 2, 3, and 4 is positive. Meaning I would have to bombard the sodium and the chlorine with energy to make things happen. So why does sodium chloride even form? Because in order for a molecule to form, we want negative energy overall. A negative means that energy is generated as a result of that formation. So again, a negative energy is what we see. Because if it's negative, it means that it is favorable with respect to overall generation. But if we just took steps 1, 2, 3, and 4 into account, sodium chloride should form, and yet we use table salt all the time. Table salt forms naturally in nature. You can find salt, lots of salt out there. So it forms. Only reason sodium chloride forms is because of the lattice energy. The lattice energy, folks, is that energy between the cation and the anion when it comes crashing together. The lattice energy is the attraction of that cation to that anion when they come crashing together. And you will note that when that cation and the anion of sodium and chloride come crashing together to form sodium chloride, we give off 787 kilojoules. So now, if you add steps 1, 2, 3, 4, and 5 with that lattice energy, the net process of making sodium chloride is a negative 411 kilojoules. It is because of this lattice energy that sodium chloride forms. Lattice energy is the driving force behind formation of ionic compounds. Because if you simply take and make ions, that requires a lot of energy to make it happen. It's not going to happen naturally. The only way it forms is because of that lattice energy. Now let's compare that with magnesium oxide. Magnesium oxide, folks, first of all, you have magnesium solid and oxygen. Magnesium is in a solid form, oxygen is in diatomic form. We have to take the magnesium solid and convert it to magnesium gas through sublimation. That's going to require 148 kilojoules of energy. We have to take that oxygen, and we have to separate that oxygen molecule by breaking the oxygen double bond oxygen, which is 249 kilojoules of energy. We then have to take the magnesium and do the first ionization energy, which is 738 kilojoules of energy. We then have to take that magnesium plus 1 and do the second ionization energy, which is an additional 1,451 kilojoules of energy. And then for our oxygen, oxygen actually has to undergo 2 as well. It has to undergo oxygen going to O minus, which is its electron affinity. It's a negative 141. But to go from O minus to O2 minus, that requires even more energy. Magnesium oxide should not form if we only look at all of this that's going on. We only look at the energy to get it to Mg2 plus and O2 minus. Magnesium oxide will not form. The only reason magnesium oxide forms is once you get it to Mg2 plus and O2 minus, those two ions come crashing together through that electrostatic attraction. And that electrostatic attraction is the lattice energy. And that lattice energy is 38,045 kilojoules. That would be technically negative. I don't know why they showed it as positive. Would be negative. So once we take into account that lattice energy, we wind up with a negative energy. Yes.
Is that how we have chemical reactions?
That's how things work together. And it's all driven by that energy. And if you didn't have this lattice energy, you wouldn't make ionic compounds. Now, what do you notice about this is 3845 compared to 4 something?
Magnesium and oxygen is 3845. Whereas that sodium chloride was 787. So just rounding, 3845, I think is what I said. So MgO has a lattice energy of a negative 3845 when they come crashing together, whereas NaCl has a lattice energy of negative 787 when it comes crashing together. From these two, if you were to describe a trend, what would you say the trend is? Because this is where you're going to be tested, not with actually coming up with all those energies. Very close. Basically, what it boils down to is the higher the ion charges, the stronger the lattice energy. Folks, this has to be the case. Because in order to make Mg2 plus and O2 minus, you had to add a whole lot more energy into the process to begin with. So the only way for that compound to make is if the lattice energy is greater too. Now, really, there's two trends here. The higher the ion charges, the stronger the lattice energy. The second thing is the smaller the atom. The higher the lattice energy. This last one has to do with the fact that once you make a positively charged ion, that's an ion by itself, folks. I just showed you those lattice energy diagrams. Ions don't like it, or atoms do not want to make ions by themselves. They're not going to want to have an ion there. They would much rather be neutral. They don't want to be an ion. You have to add energy to make them ions. They don't want to do it. The only reason they make ions is because of the lattice energy, or make ionic compounds is because of that lattice energy. So if you have smaller ions, it means you're forcing a positive onto a really tiny atom. It's going to know it's going to have a positive charge. It's not going to like its positive charge. Whereas when you force an ion onto cesium, that's a huge thing. It doesn't really care what's going on as much. So it doesn't know it has that positive charge as much. So the tinier the atom, the more it knows it has that positive charge. And so the tinier the atom, the higher that lattice energy is going to be, because they want to get together quick. So these are the two trends. Hmm? So if I were to give you a problem on a test, is that what you're asking?
More so like for the future for like anything else.
Okay, so when you add magnesium oxide to water, you get milk of magnesia. That is an antacid. So that's one common use for stuff like this, is as an antacid. So, for an exam, how would you see this? Something like place the following ionic compounds in order of increasing lattice energy. The first thing I tend to do is I go, okay, so let me see. We'll keep up with some of the stuff I've already done, but let's take in and go with, and 3 and Na2O. First thing I do, folks, is I sort by charges. I will go and look at it and go +1, -1, +2, -2, +1, -1, +3, -2, +1, -2. I'll go in and add my charges to all my atoms. I'll make note, I want my strongest over here and my weakest over here, just so that I know. So +1s are going to be weaker, so I'm just putting them over here right now. That then I would put in that Na2O, and then the MgO, and then the Al2O3. That would be the strongest because it has the highest charges on ions. So my answer would wind up Al2O3 MgO, Na2O, and then I would go with NaCl before NaBr because NaBr, the bromine is larger than the chlorine. Oh, no, I am looking at I just look at the charges. So a +3 is bigger than a +2. A +1 is smaller than a +2. I am just looking at the charges as they are. I'm not looking at the magnitudes of anything. Okay, folks, the homework on active, actually, I think I got it where you get tables to look at. So hopefully you can spot these trends in those tables with the lattice energies. And with that, I will see you on Thursday, and we will begin balancing reactions and getting into reaction chemistry. Yes? I don't know if there's one of these. I know that it asks, I mean, there is in a sense, but it gives you the lattice energies. It's not, now I know my optional homework has some like this.